Dear President Joel Mezzo, dear colleagues, dear Lars, it's my great pleasure to welcome you to this inaugural lecture of Professor Lars Lindemann. My name is Gabriela Hulk, and I currently serve as the department head of the Department of Information Technology and Electrical Engineering. Let me introduce Lars before he gives his talk. Lars completed his PhD in electrical engineering at KTH Royal Institute of Technology in Stockholm in 2020, where he developed the foundations of his research at the intersection of control theory and formal methods. From Stockholm, he moved to the University of Pennsylvania as a postdoctoral fellow in the Department of Electrical and Systems Engineering, working closely with George Papas in one of the leading groups worldwide in autonomous systems and cyber-physical systems. He then joined the University of Southern California as an assistant professor of computer science, where he founded and led the Safe Autonomy and Intelligent Distributed Systems Laboratory and served as Associate Director of the Center for Autonomy and Artificial Intelligence. His work during this period garnered significant recognition, receiving multiple awards for his work. It was then from USC that ETH Zurich called him, and he took up his current chair last year. Lars' research sits at the fascinating crossroads. He brings together systems and control theory, formal methods, machine learning, and applied statistics to answer a seemingly simple question: how do we build autonomous systems that are not just capable, but provably safe? In a world where machines are increasingly acting without direct human oversight, self-driving cars, navigating urban intersections, drone swarms, conducting aerial surveys, intelligent transportation networks coordinating in real time, the stakes of getting this right are high. Lars' work addresses these challenges, developing mathematical frameworks that offer rigorous, quantifiable guarantees of safety, even when the system's environment is uncertain, dynamic, and only partially known. A particular focus of his recent research is the use of conformal prediction, a powerful statistical tool for uncertainty quantification, to provide formal safety certificates in planning and control algorithms that hold without assuming a specific probability distribution over the environment. This makes his methods remarkably robust and practically deployable, bridging the gap between the clean assumptions in a laboratory environment and the messy reality of the world outside. With this appointment, the department strengthens its research in system theory, control technology, and the computational sciences, while deepening interdepartmental links across robotics, autonomous systems, and machine learning. Today, he will share his vision with us in his inaugural lecture. Please join me in giving a warm welcome to Professor Lars Lindemann.
All right. Hello, everyone. Welcome. Thank you for coming here. Thank you, Gabi, for the kind introduction. It's my great pleasure and honor to be here today to give my inaugural lectures on the foundations of safe autonomy. I have three goals with this lecture. First of all, I would like to introduce you to the world of autonomous systems, and I would like to talk about the challenges that we face when we talk about or when we analyze their safety. Second, I want to hopefully convince you that logic, learning, and control can build the foundations of safe autonomy. And I want to share some of the work that we've been doing in my lab over the last couple of years. And lastly, I would like to take the opportunity to provide an outlook of what autonomous systems and autonomy can bring for us as a society in the future and the next years. First of all, what are autonomous systems? Well, at the end of the day, they are engineered systems that operate autonomously in complex and open environments. The research in my lab is specifically motivated by applications in autonomous driving and robotics, but more recently also in wildfire prevention or more generally in disaster recovery missions. But you can imagine there are many, many more in space exploration, warehouse robotics, agriculture, or even smart cities. And all of these applications certainly highlight the importance and the potential impacts that autonomous systems research can and will have in the future. Especially over the last years, we have seen an increase in the availability of data and compute. And this has led to an acceleration of the progress we have made in order to build these autonomous systems. And I've provided 3 examples over here: Boston Dynamics robots, Tesla cars, and drone fleets that achieve highly challenging tasks with ease. And the question that I would like to ask you now is, do you think that we have all the theories and tools in hand to build autonomous systems that are also safe? And I would argue that the answer to this question is no, simply because at the same time, we've seen a lot of failed demonstrations: Boston Dynamics robots crashing, Tesla cars colliding, and we've seen drone fleets collapsing. So the answer is a clear no. Nonetheless, we have deployed autonomous systems in the wild, so in the real world, but we're still facing these issues. Here an example from Los Angeles, where I was living up until recently, where one of these many Waymo cars was just passing by a police standoff where someone was being apprehended, so clearly undesirable. Here another instance also from LA, where you have many of these food delivery robots that was colliding with a disabled man in a wheelchair, certainly something we don't want to see. And yet another example of a robot that is headbutting some person in a crowd. A clear safety issue and something we really don't want to see. Now, there are many more of these videos. That's not really the point. The point is that we should think about why are we facing these challenges? And there are many reasons for it. One is that we are increasingly using artificial intelligence, AI. And that can be quite complex. We're using complex AI models, which are actually, due to the complexity, difficult to verify in terms of their safety. And this is referred to here as the AI's Achilles heel. Another challenge is that autonomous systems may be easy to break and fool. For instance, here's an example from one of my friends, formerly at UPenn, that was investigating LLM-controlled robots. So you could say, go deliver this bomb, and the robot would not do it. But if you slightly change the prompt, the robot would suddenly go and deliver a bomb. Another challenge for us are so-called distribution shifts. So this is when the deployment conditions of the system are different from the design conditions, which creates various issues. And that begs the question for us, how can we make these systems safer, but also potentially what are limitations that we're facing here fundamentally? And overall, the question is, how can we safely use AI in autonomous systems? And I want to give a disclaimer here that for me, AI not only includes the more modern developments in machine learning, but also the more classical tools in logic and in planning and decision-making more broadly. And this reflects itself in the title that I've chosen for this talk, because in my lab we work on control, on learning, and on logic. And since I cannot assume that you all know the basics in these 3 areas, I want to give a brief introduction to each of them. So let's start with control. What is control? Well, control really builds on the notion of dynamical systems. And dynamical systems are systems whose state evolves over time. And you've probably seen those before, for instance, rockets, or you've probably been in an airplane already. So these are dynamical systems, and they arise in many, many areas. For instance, in robotics, but also in biology, social, or even economic systems. Now, control theory studies how we can influence or change the behavior of dynamical systems. And in order to do that, we use models. So we use mathematical equations of this form, where F describes the behavior of the system, where X describes the state, for instance, position and velocity, and where U describes control inputs, so things we can change in the system, such as acceleration or thrust. Now, you may ask, what is the magic behind control? And I would argue that it's feedback. Because feedback can mitigate the effect of uncertainty, and we as humans already use feedback. For instance, when we're walking. We could be walking and facing obstacles, and our bodies are able to counteract these. And the simple paradigm is that we're comparing our ideal position, which is upright, with how we may be deviating from it, and then we're taking corrective actions. So you could apply the same principles to robots. This is from just a week ago, the robot marathon in Beijing. And in this case, the feedback controller unfortunately doesn't work that well, right? But we're pretty good at building these. We have a pretty good understanding of how we can build feedback controllers for bipedal systems. We have some expert here at ETH. Now, feedback creates so-called feedback loops, where at the core, we again have dynamical systems, uncertainties, and we have these feedback control laws that take states X And then they compute the control actions based on that. And as mentioned, it is very powerful because it provides robustness to uncertainty. It allows real-time operation and adaptation. And it comes with very powerful analysis and design techniques that provide strong safety and performance guarantees. But there are some drawbacks. For one is control typically considers very simple requirements, so no high-level specifications, and it relies on models. And in that way, it connects and complements really well with learning and logic-based methods. Let me next talk about learning. Machine learning, at the end of the day, enables computers to learn from data to make predictions and decisions without being explicitly programmed to do that. The goal in supervised learning is the following. You want to predict an unknown outcome, let's call it Z, from observed inputs, U. And you could think about it the following way. The inputs could be images, and the output could be the correct label, cat or dog. And what we do is we select a model mu that takes an input and predicts an output Z hat. And we train or learn this model to minimize an expected learning error. So we minimize, here it is, we minimize the expected value over some data that we're receiving in regard to the error of the true label and the predicted label. And these learning algorithms at the moment are really the main driver in the AI trends, because what we can now do is we can use more complex models, more data and more compute. We can generate synthetic data using so-called generative models, and we can even deal with high-dimensional data such as language or videos. And just to give an example, I actually sat down while I was preparing this presentation, and I generated this image within just 5 minutes. Very powerful, we're all using it to some degree already. But there's a challenge when you want to use machine learning in autonomous systems. Many challenges that we're facing when we move to dynamics. Particularly in autonomous systems, we usually look at these type of block diagrams that I want to briefly explain. We have dynamical systems, in this case a car. We typically have environments that may contain other cars or pedestrians. And we typically have sensors such as camera or LiDAR. And then we have a stack of perception and prediction algorithms to estimate states about the state of the car and the environment. And then we have algorithms for planning and control to feed back control inputs. And we may be doing this over and over. And there may be many learning components in these loops these days. For instance, object detectors to detect objects and assign semantic labels. We may use learning for predicting, for instance, pedestrians at an intersection. Or we may use learning to directly learn models or decisions. And while this slide here is tailored to autonomous driving, you could make the same case for wildfire prevention, where you want to detect wildfires, you want to predict their spread, and you may want to mitigate their effects by using drones. But the key challenge here is that because you're using quite complex models, that you cannot analyze analytically the safety of these systems anymore. Lastly, I want to talk about logic. Why should we consider logic? Logic gives you a way to express requirements for autonomous systems. There are other approaches. You may have heard about reinforcement learning, where we have to choose a reward, and we maximize this reward function. But what can happen is, if we choose the wrong reward, we may get behavior like this. So, wrong behavior. Other approaches consider imitation learning, where we learn from human demonstrations, but there the question is, how do we get good demonstrations and enough of them? Other approaches could be based on large language models, but we all probably face the issue of picking the right prompt. And this raises questions, for instance, how can we unambiguously specify system requirements? How can we automatically verify and enforce such requirements? And how can we deal and quantify uncertainty for these requirements? I argue that temporal logics is something that is useful because it provides a principled way to express requirements. For instance, you could tell a drone to always avoid region E, periodically every hour inspect regions A and B. Whenever the battery is low, the drone should recharge eventually in C or D, and it should turn on communication between some time. These are specifications you can mathematically write down in temporal logic. And it's precise, unambiguous, and it's machine interpretable. Temporal logics have been used across a variety of domains, for instance, to formulate traffic rules. This has been done here, like the Straßenverkehrsordnung. It's been used in medical application for pancreas monitoring, and we've used it with collaborators from Toyota Research North America for monitoring smart cities. And the cool thing these days is that you can actually use LLM to act as an interface between natural and formal language. So you could have a requirement here in English, you feed it into an LLM, and you get a temporal logic specification out of it. Now, in my lab, we put these things together with a goal to design verifiable control framework for autonomy, along with efficient computational algorithms. We broadly have 5 directions that we look into: data-driven control, risk-aware autonomy, verification of systems, temporal logic-based control, and multi-agent systems. And what I want to do today is I want to move from left to right and give you some teasers of these areas. And the way you can think of it is that we will increase the level of autonomy when going from left to right. On the left-hand side, we consider simple specifications like stay inside the lane, while on the right-hand side, we may have multiple agents and specifications such as those you may need in a warehouse. So with that, please follow my journey over the last years. I'll give you some insights about the research. We first need to define what we mean by safety. In this case, we define safety if this robot here can, or if we can control it to stay within a safe declared set calligraphic C. So if we can always keep the robot inside this blue set. There are many methods in this field, ranging from handcrafting safe control laws to computational approaches. These approaches are either limited to simple systems, or the computational complexity does not scale well with the dimension of the problem. So in summary, finding these safe control laws, even though there exist so many approaches, is really challenging. And what we ask ourselves, can we build up on those and leverage data and machine learning on top to have some gains and be able to design better control laws? What we did in one of the projects is we used something called control barrier function. This slide is a little more mathy, but I'll try to walk you through it more carefully. We assume that we have a dynamical system that is described like this. And we also assume that our safe set, this blue region, is described by a function h. So all states x, where h is non-negative, belong inside this blue region. And now we need to think about what does the robot have to do in order to stay safe? Well, at the end of the day, whenever the robot is on the boundary, we need to be able to select control inputs to either push the robot inside or along the boundary. And this is equivalent to assuming that there exists a use such that the time derivative of h is non-negative by the definition of the safe set. And we can make this intuition precise by calling h a control barrier function if we can select such a control input such that the time derivative is greater than minus an increasing function that is 0 at 0 of h of x. And because it's 0 at 0, we exactly recover this condition. And the cool thing is, if we can show this mathematically, then we have found a safety filter and we're good to go. The bad news, however, is that these are incredibly hard to construct. And again, that's where we come in, and we were asking the questions, can we learn them? To give you a high-level overview, what we did is the following. We assume to know the dynamics, and importantly, we assume to have available a set of expert trajectories, which are these spaghetti trajectories that are assumed to be safe. They are inside this red box. And we feed these two into an optimization-based algorithm that we're designing here, and with a goal to find a safe control law. Indeed, what we're doing is the following. We're learning a function that under-approximates the operating region of the expert, shown in blue, and has the property that we can always select a control input to keep the system inside. The key properties of our algorithms are that we provide learning algorithms for control that have verifiable safety guarantees. We can even deal with perception uncertainty of autonomous systems, and we can extend this framework to quite complex, unknown, and so-called hybrid systems. Let me give you some demonstrations. On the left-hand side, you can see a car in the autonomous driving simulator Carla. And here we have an expert controller that we just used. We knew that was safe. And we used it to collect some data. On the right-hand side, you can see our learned control barrier function that also keeps the car safe. And importantly, whenever the car is about to leave the lane, the controller kicks in and keeps the system inside, imitating the expert to some degree. We've also implemented this on a bipedal walking case study, where you have a passive walker that walks down an inclined ramp, and you could control this little guy in the hip or in the ankle. But if you don't do this, you see the walker just falls down after a couple of steps, unsafe. So what we did was we picked an energy-based controller from the literature. We used it, again, to collect expert trajectories. And then we trained a neural network, and you can see the result here. The correcting control actions are shown in blue. The system is kept stable and safe. With that, I would like to move on to the next talk. Now we talked about low-level safety. The next step is to consider uncertainty and potentially learning components that we're adding to this loop. So let's take, again, a look at this feedback loop in autonomous systems. And the question I would now like to ask you is, how do we reason about safety of such high-dimensional systems? And by high-dimensional, I mean that we may have machine learning components in here that may be quite complex and hard to analyze analytically. Now, there are some approaches in the literature, some exact techniques that can exactly quantify input-output properties of these machine learning models or systems that are controlled by these learned components. However, the drawback is these techniques have scalability issues. They don't apply to the problem in hand. And that has motivated techniques that use relaxations. They are not exact anymore, but the drawback here is that they are typically overly conservative and also not applicable. Now, what we would like to do is we would like to navigate this trade-off between scalability and conservatism. And on top of that, we would like to deal with uncertainty that enters the system, such as disturbances on the car, noise on the sensors, or randomness in the environment itself. And we ask ourselves, can we use efficient statistical tools from statistics to reason about safety of such systems? And it turns out that conformal prediction is such a tool that is applicable and useful in this case. Conformal prediction has been quite popular because it provides uncertainty quantification under minimal assumptions. What I mean by that is the following: it's distribution-free. So if we're again in a supervised learning setting where we have inputs and outputs that are drawn from some data distribution, we don't need to make any assumption on the data. It could be arbitrary data that we're receiving. At the same time, we don't need to make any assumptions on predictors that we're using. So, for instance, if we have mu here and it's a neural network or any more complex model, we can deal with those. What we, however, need is the availability of an IID, so independent and identically distributed data set of input and output pairs that are also drawn from this distribution. And the goal of conformal prediction then is the following: you as a user pick a failure probability delta, and conformal prediction gives you a region C, so that with at least a probability of 1 minus delta, a new test data point is contained in this region. Just to illustrate this, assume you're given 3 images, shown here, and a classifier, okay? Now, the first image is really easy to classify. It's a clean image, and in this case, we can immediately see it's a fox squirrel. In this case, the prediction region contains only 1 label. Images 2 and 3 are more difficult to classify. In this case, the head is actually chopped off. And in those cases, the prediction region C may contain 4 or even 6 labels. And we use this to reason about learning-enabled components, and I want to show you one instance of those. Here we considered a problem where we did safe control design in dynamic environments. The problem is the following: we would like to compute control inputs so that a system, our car, avoids dynamic agents in the environment, so other cars or pedestrians, with a probability no less than 1 minus delta. And the way we go about this is as follows. We assume we have some offline data of how pedestrians, for instance, walk at an intersection. And while our car is operating, we assume that we can measure the state, so position and velocity of the pedestrian, and maybe we have access to a history of those as well. And we use a trajectory predictor that could, for instance, be learned from data to make predictions about the future behavior of the pedestrian, here denoted by y hat of t plus 1 and y hat of t plus 2. Now, the big elephant in the room is, if we're using, for instance, learning components, how good are these estimates? They may be accurate, but they may sometimes also be terribly bad and affect the safety. So what we're doing is we're using conformal prediction, and we build in blue these prediction regions that are statistically valid, meaning they contain the future behavior of the pedestrian with 1 minus delta probability. And what we do next is we forward these regions to our robot, where we assume to know the dynamics, and we design a controller, in this case, a model predictive controller, to keep the system safe. Meaning that we have a safety constraint C that affects our system and the environment Y, for instance, keeping a minimum separation between the two, and we ensure that this is non-zero or non-negative with high probability. Now, these algorithms are quite lightweight. The good thing is they're also predictor agnostic, so we could use any predictor here, more classical predictors or even generative models. We can deal with distribution shifts, which I mentioned earlier, and we can also deal with temporal logic constraints if we want to. Just to give a visual, here you see a toy example where a robot is navigating around dynamic agents. And you see initially we form these now in green prediction regions that shrink over time, which allows us to plan an optimal path for our robot. We've also implemented this again in this autonomous driving simulator, where we have pedestrians that spawn at random positions, go to random goal locations, and walk at random speeds. And the main goal of this was to empirically validate if our theoretical safety guarantees hold as well. If you're interested, we have a survey paper on this topic, on conformal prediction, that was recently published. And we have another survey paper that looks at risk in robotics more generally using so-called tail risk measures. So it's a very active field at the moment. Moving on. Now we've talked about low-level safety, we've talked about uncertainty in learning components, but we haven't really talked about more complex specifications, temporal logic specifications. And that's what we want to do now and verify systems. Looking again at this block diagram for an autonomous system, I elaborated before that safety verification can be challenging. And this is because these techniques technically explore all possible system behaviors, which can be expensive. And that has, in some fields, led to a misperception that safety verification is intractable. But I would argue that there are actually tools, verification tools, that are tractable. Lightweight tools for verification, one of them being statistical verification using tools like conformal prediction, where we again use data to provide confidence. But there are also so-called runtime verification approaches that are also sometimes called monitoring, which are online verification approaches that really prune the search space and are more efficient. And here in this sample project, we were asking, can we use statistical tools to design runtime verification algorithms? And what we particularly did is we designed predictive runtime verification algorithms, where while the system is operating, we want to predict into the future and get confidence about how safe the system will be. More mathematically, what we do is the following. We assume that we have made observations of our system up until the current time t, and we would like to compute the probability that a safety function rho phi is non-negative. And this raises some questions. For one, how do we systematically express this safety function? Also, how do we design efficient, so real-time capable and interpretable runtime monitors? And how do we get statistical guarantees? Now, to answer the first question, the good thing about temporal logics is they can be translated into such a safety function rho phi. And I want to give you some easy examples. For instance, if we look at this temporal logic formula here, most of you may not know how to read temporal logic, so I'll translate it to you. This basically means eventually between 3 and 5 seconds, the state should be between 2 and 3. Here, it means that the signal should be in this green box for at least one time, and this is satisfied. And we get this safety function value of 0.5. Importantly, it's positive, and it gives us some safety margin of 0.5. Now let's look at another specification. This one reads as follows. Always between 2 and 6 seconds, the state x should be between 0.5 and 6. Meaning at all times, the signal should be inside this green box, which is satisfied here, giving us a positive safety function, but only slightly positive in this case, small safety margin. And if we shrink this green box, so we lower the bounds here, we see that we actually violate the specification and we get a negative safety function. And this safety function provides us information about the quality of satisfaction or violation, and we will use it for monitoring. The idea is as follows. We again assume that we have collected some data from our system. While the system is operating, we again observe what it's been doing so far. We again use predictors to make predictions about the future. And now we evaluate this safety function on the observations we've made already, as well as our predictions. And similar story as before, the question is, how good are these safety estimates? They may be completely wrong. And we're using conformal prediction once again to devise different runtime monitors that provide lower bounds for the true safety function in terms of the predicted safety and some calibration constants. These algorithms are lightweight and they are interpretable, quite efficient, and they again come with guarantees. We validated them on a set of case studies. One that I'm showing here again is on autonomous driving. On the left-hand side, we have an imitation learning controller. On the right-hand side, a control barrier function-based controller. And we answer questions such as, can we even predict unsafe behavior? And the answer is obviously, yes, we can. And we can even use the tools to select which of these two controllers is the safest one. Moving on to the last part, I would now like to ask, can we even enforce these complex specifications, these temporal logic properties? And can we even do this for so-called multi-agent systems, where multi-agent systems are really systems that not only contain one agent, but multiple of those. Consider, for instance, multi-robot systems. Feedback control, as introduced in the beginning, gives us approaches for simple stability and invariance tasks, so very low-level requirements. But we learned that temporal logics give us a formalism that can express much more complex tasks. On top of that, we have multi-agent systems, which, if we do it right, can coordinate to achieve complex missions. And the question here is, can we design multi-agent control systems that satisfy such temporal logic tasks? There's some existing work that posed this problem as an optimization problem, where we want to enforce our system dynamics. We want to maximize our safety function and make sure that it's positive. Unfortunately, these approaches are extremely difficult to solve. They are non-convex and non-smooth. And they, importantly, don't scale to multi-agent systems. They're computationally intractable. There are other approaches from the more computer science community where we use automata, so finite state representations, for the system as well as the specification. But a similar story here, they are subject to the so-called curse of dimensionality, where the search space blows up. And that again implies that these techniques are intractable for multi-agent systems. So for us, the question was, can we instead design efficient, low-level feedback controllers that scale to even larger number of agents? And the way we went about this is as follows. For single-agent systems, we decomposed the task, the complex task, using offline planning in sequence of simpler tasks. And for these simpler tasks, we designed transient or time-varying feedback controllers, so you see T over here, that can implement these simpler specifications. Now, for multi-agent systems, we then also designed decentralized control law, where each agent is computing its own control actions. And these control laws are quite efficient, and to do that, we used time-varying control barrier functions or technologies that are called prescribed performance control. And it reduces the complexity significantly. Now, my PhD advisor, Professor Dimos Demarogonas, and I, we've written a book on these, and if you're interested, please take a look. But I want to show some experiments here from the lab where we enforced navigation specifications, formation control specifications, and more complex temporal logic tasks. And at this point, I would also like to give a shout out to my friends at KTH who have pushed the boundaries even further by bringing in humans in the loop, doing human teaming, for instance, here in warehouses for complex logic specifications, or even in the real world for agriculture applications. Next and last, I would like to conclude this talk and provide an outlook for what's to come in the future. First of all, a few key takeaways. Autonomous systems are already transforming our everyday lives. I have a video here that I took myself when I was still living in Los Angeles of one of these Waymo cars. There's a charging station behind, and they're everywhere. I've used them, many people use them, they're affecting everyone's lives already, making commute to work a little more convenient because maybe you don't have to talk to a human driver. Maybe you don't want to on some days, right? Another example, I talked about these before, food delivery robots. Especially Friday evenings, there are a fleet of these robots delivering food to everyone, also making life a little more convenient. And a more classical example, this was actually taken in San Diego, of airplanes. More sophisticated technology, but highly automated and already really, really safe. We also learned that AI has enormous potential, but that safety is really a bottleneck when we want to deploy these systems in the real world. But we also learned that we actually have efficient tools to analyze safety despite common misperception. And I hope I was able to convince you that logic, learning, and control can build the foundations of safe autonomy. The follow-up question on this is, can we move on then? Are we done? And I would argue that this is just the beginning of an era of autonomous systems. There are many opportunities. There are more exciting areas: urban mobility, disaster recovery. I talked about wildfire prevention or earthquake recovery, space discovery, and many, many more. But I would also say that we're not really there yet for many reasons: technological reasons and non-technological reasons. For instance, about large-scale deployment, can we imagine to have Waymo cars in Zurich soon? And the answer is probably not. Indeed, I talked to one of the Waymo people 2.5 years ago when Waymo cars were already operating in San Francisco, and they tried to deploy the cars in LA, and it didn't work. So what they had to do was use human drivers to collect data for almost 10 months. And that's time-consuming, and it costs a lot of money. And the question is, are there financial incentives to do this in Zurich, where public transportation is really good? Probably not with the current technology. Another one is certification and liability. How do we quantify risk for these systems, and how can insurances do this? There are many legal questions associated with autonomy. Another bottleneck is a safety versus performance trade-off that I experienced myself. Self-driving cars are very slow because they need to be safe. So if you take a Waymo to work, it can take twice the time. So if you have a long commute, you will drive for a long time. And I talked about this a lot, technological maturity. Just another recent video where you have 2 Waymo cars and they fail to coordinate. It's a common issue, actually, that when you not only have one but multiple, that they don't know what to do. And here, yet another very recent example where one of these food delivery robots is crashing into glass and shattering it. And this brings the question, how do we increase technology transfer from universities to industry? Like I said, safety and reliability is still one of the key bottlenecks. There was very recently published an AI report that is yearly published from Stanford. And what they do is they track how AI is being tested ambitiously across reasoning, safety, and real-world task execution, and they had some takeaways. One being that AI models can actually win a gold medal at the International Mathematical Olympiad, but sometimes they cannot reliably tell time. They also saw that robots still fail at most household tasks. So when they need to generalize in real environments, they're actually not that good. And responsible AI is not keeping pace with AI capability. Here, importantly, with safety benchmarks lagging and incidents rising sharply. On a good note, though, Switzerland is doing amazing. If we look at the total number of AI authors and inventors, Switzerland is 11th. If you normalize this by the population in Switzerland, which is quite small, as we know, we're first. And that's amazing. I'm really glad to be part of this community and to be able to contribute in the future. Now, what's next for me over the next 2 to 3 years? I want to look more into issues that happen when we talk about safety in the real world. So when design and deployment conditions differ, for instance, when environments change, when we use data from simulators, photorealistic simulators for the real world, or when we have interaction between our machines and humans. And we've made some initial progress there for methods that do safety transfer with my student Omid, who's also here in the audience. Another thing we will look into are time-critical systems, where the when is just as important as the what. For instance, if you think of Deutsche Bahn, I'm sure you've taken Deutsche Bahn trains. They are more often than not delayed, even though it got slightly better, I feel, over the last 2 years. But there are also safety-critical systems where time is important. For instance, airplanes, runway incursions, or mid-air collisions if the timing is wrong. And even wildfire prevention is a time-critical system because you want to detect fire within timelines, right? You don't want to wait forever until you detect a fire. We've also made some progress there with my postdoc Oliver, who's here, on quantifying robustness for such systems. And lastly, we want to broadly look into multi-agent systems. So how can we coordinate swarms of AI-enabled systems? And there we investigate efficient neurosymbolic design approaches. Lastly, I would like to end this talk by posing some questions that I personally may not have an answer to. I may have opinions, but I think these are questions we should all be discussing. The big elephant in the room is, will AI make research obsolete, or will AI just be a powerful tool for us? I personally think it will be a powerful tool for us that we need to learn how to use responsibly. And that's the next point. How do we do that? How do we particularly interact with our students and PhD students to teach them how to use AI responsibly, right? How do we write papers, verify results when we use AI as a tool? And this is commonplace. Everyone is using AI to get an opinion, to maybe verify, double check, or get some solution hints approaches. Another issue is, how do we prevent abuse and low quality mass productions? In my field, there's an increase in the number of papers that are being put out and published, but are they really all good in quality? I would question that. And related to that, can the peer review system survive this AI scale publication? Can we change the peer review system to keep up, and how should we do that? Another important point, I believe, is how should evaluation change when paper production scales exponentially? I'm talking about PhD students. How should we evaluate them? How should we evaluate postdocs on the job market? And how should we evaluate people like me who are in the tenure track, right? When some people are just churning out papers. What are the metrics? And one important point, and people here at ETH actually work on that scientifically, how can we verify AI-generated content? And lastly, but also very importantly, what is the role of universities when teaching becomes automated? How will teaching look like 10 years down the line, maybe when AI can explain things much better than I can do? With that, I would like to thank and end this talk. I would like to thank my PhD advisor, Dimos and Jana, who have been amazing. I built all my own foundations at KTH. I would like to thank George, Nikolai, and Manfred at UPenn. Manfred, you probably know. He's been here at ETH for a while. I had an amazing time at UPenn and learned a lot. So these were also good foundations, especially when it came to machine learning and integrating these. I also want to thank my colleagues and friends at USC, Joe Deshmukh, Gaurav, Madi, my biking friend, Mihailo, Stephen, all very close collaborators. And last but definitely not least, I want to thank Florian and John for their support in the first months, as well as Sabrina for keeping the lab together. And I would obviously like to thank the Automatic Control Laboratory. You all are amazing. I'm really glad to be here. I would also like to thank my team here, and I still have a few students at USC. They're all amazing. I'm really fortunate to be able to have such talented people. I would like to thank many other academic friends and collaborators. I hope I got everyone on the slide here, probably missed someone still. And I would like to thank funding agency, especially ETH, for very, very generously funding my research here and making my life a lot easier so that I can focus on the important things. Thank you so much.